This next section is actually a very critical one for you on your exam. The same content in different form shows up, of course, on the Step 1 exam, but also the Step 2 CK and also the Step 3 exam. Because frankly, if you don't understand screening test, it's hard to participate in the current practice of medicine. Screening tests are a way of understanding not just the numbers, but what the numbers mean. Most exams have several questions in screening tests. Some have many questions. This is content I want you to put as your goal to get so you have it fairly comfortably. So when you look at the exam screen and a question is up on screening test, your reaction is not, oh no, a screening test question. Your reaction is, yay, a screening test question. That's when you know you have the content at the level you need to have it. Screening is crucial in medical practice, but let's begin with the basics. The basics begin by simply asking, why do we do screening in medicine? Why do we do screening? Well, the answer is simple. Because we're not God. If we were God, we'd simply look down from on high and go, you're diseased and you're not. And being God, we'd be right about these things because God's perfect, knows all, and sees all. We are not perfect. We don't know all, and we don't see all. And so when we're trying to decide who has and who doesn't have disease, we invent for ourselves a test. The test classifies people as positive, we think they're diseased, or negative, we think they're disease-free. Well, now wait. Once you realize we have a test, and once you realize we have a real standard of affairs, people that are diseased or non-diseased, there's an obvious question before us. Namely, how good is our screening test? How good a match do we have between the gold standard, what we use to determine reality, and the actual screening test classification that we get from our assistant? Well, there's a number of ways to begin to look at this, but by far the simplest is to construct a simple 2x2 table, as we've done right here. Here we have disease, present, absent, and then we have screening test results, positive or negative. Please note, positive means we think they have the disease. Negative means we think they're disease-free. And so positive doesn't mean a good thing. It actually means a bad thing. We think they have disease. Negative doesn't mean a bad thing. It actually means a good thing. It means we think they're disease-free. You can see we have numbers in our table here. We have 80, 20, 40, 60. These are the numbers in the cells that constitute our typical 2x2 table. But before we proceed using this table, we have to complete the table, because the table is not yet complete. See, 2x2 tables such as this are made up of numbers in the cells, yes, but also of, well, marginals. Marginals are the sum of the columns and the sum of the rows. And so, looking at our table here, you can see the first column sums to 100, 80 plus 20, and the second column also sums to 100, 40 plus 60. You can see the row marginals are, again, fairly easily derived, 120 and 80, simply adding across the cells. One final number completes our table. We need to know the total for the table. What's the total for this table? Well, obviously, 200. 200 is the table total, adding across or down, not both, adding across or down the marginals. Now, what letter do you use to represent the total for the table? The total is represented by the letter N. N means here and elsewhere in epidemiology and statistics, the sample size, the total number of people that we're talking about. Okay, with the marginals in place, we're now ready to go through and deal with our table. Now, many textbooks at this point will have you go through and label your cells A, B, C, D, and thus labeled, execute formulas based on those labels to derive, well, core screening test values, things such as sensitivity, specificity, positive, negative predictive value, and accuracy. If you know how to do this by the ABCD method, you're in fine shape. That method will get you the right answer, and you'll get the right answers you need on the exam. But if you don't know how to do it by the ABCD method, here's my advice. Never learn it like that. Because experience shows in the heat of battle, in the middle of the exam, or indeed when in the face of clinical practice, remembering which cell's A, which cell's B, which cell's D, it's hard to do, remembering exactly what the right letter is for the right cell. And if they rotate the table on you, make it so it's not in the current format, but we flip and put rows and columns in different organization, then labeling the cells A, B, C, D gets even harder. So forget A, B, C, D, the arbitrary letters. Let's call the cells their actual, that is, their true names. Look, everybody here in the top row got a positive on the test. So everyone in the top row is, of course, a positive. Please note, There's no question about whether or not they're positive. It's what they got on the test. It's a given empirical fact. They're positive. Please note, everybody in the bottom row of this table got a negative on the test. And once again, an empirically given fact. There's no question they're absolutely negative. It's what the test says. But now the question is, given what the test says, what's the agreement between the test and the gold standard of reality? Well, in the upper left-hand cell, we have present and positive. Well, that's an agreement, so we call that true. In the bottom right-hand cell, we have absent with negative. That's also an agreement, and so that's true. And the off-diagonal cells, positive with absent, present with negative, we call those false. And now you have your cells labeled by their real names: true positive, true negative, false positive, and false negative. Now look, when you're labeling your cells, do what I just did. Don't look for the true positives. No, that's too hard. Look for the positives that are true. Reverse the letters. You have a much easier cognitive exercise here. Don't look for the false positives. Look for the positives that are wrong, therefore false. In short, make sure you nail positive or negative first, and only then turn your attention to true or false. Another comment. Don't just walk away from here going, I understand this. The true positives are in the upper left-hand corner because they may not be on your exam question. It's a favorite gimmick of the question writer to rotate the table on you, to, well, switch the present and absent columns or take disease and put it on the side and put the test results up on the top. If you're using the ABCD method and they rotate the table on you, this could be very problematic. If you're using the method I'm going to describe here, where you label the cells true names, rotating the table doesn't even slow you down a heartbeat. This is the basic core subject matter we're going to use for our calculations. Now we're next going to turn our attention to how to do some basic calculations, but before I run through those with you, I need to alert you, increasingly on your Step 2 CK exam, it's not just about calculation, it's about comprehension. That is, they want you to know not just what the formula is and how to derive the right answer. What they want is, well, they want to make sure that you know what it means. What are you getting? Why you're doing this? And then, as we move forward, how you're going to interpret this to your particular patient. Let's begin by talking about how we're going to remember the formulas that you need, however. You're going to remember the formulas you need for this exam. I'll do this again. You're going to remember the formulas you need for your screening test by a very simple rule. One rule gives you all the formulas you're going to need. What's the rule? Here it is. Trues on top and divide by everything. I'll say that again. Trues on top, divide by everything. One rule gives you 5 formulas: sensitivity, specificity, positive, negative predictive value, and accuracy. One rule gives it all. Trues on top, divide by everything. Let me try to illustrate that as we move on to the first of our screening test parameters, sensitivity. Sensitivity. Now before we do the calculation, we have to pause and remember what sensitivity is about. What is sensitivity? Oh, easy. Simple 2-word definition. Sensitivity is about detecting disease. I'll say that again. Sensitivity is about 2-word definition, detecting disease. If I have perfect sensitivity, I found all the disease that's out there. I've been perfect at identifying all the diseased people. Sensitivity, therefore, is about disease. I can therefore ignore the right-hand column of my table where all the non-diseased people are, and now I'm just going to focus on the left-hand column, just where the diseased people are. Present means disease here. Once I've eliminated what I don't need, now I'm going to apply my rule. What's the rule? Trues on top, divide by everything, which translates, of course, to true positives, trues on top, divided by true positive plus false negative. True positive divided by true positive plus false negative. Another way to say that is the true positives divided by all the diseased people. Please note that everything in that calculation is a diseased person. Of course it is. It's sensitivity. It's all about disease. The formula is therefore straightforward and the calculation is easy as well. When I plug my numbers in from the table, I find 80 divided by 100, or 80% sensitivity. 80% sensitivity. What is this? Good, bad, indifferent? Well, it's actually pretty good. 80% sensitivity means if there's 100 diseased people out there, I find 80. If there's 10, I find 8. Now that's not as good as we'd like to have it be, but it's certainly better than a 50-50 guess, which is what we have without using any screening test at all. What we'd like to have for screening test parameters, of course, is well into the 90%. 90, 95 is what we're usually looking for, but the rule in medicine is not to judge yourselves against perfection, it's to judge yourselves against what else you got. And if you didn't have any better test than this, 80% sensitivity is giving you great utility, we'd find 80 out of every 100 diseased people instead of the 50 out of every 100, which would simply be a random guess. Sensitivity is easy. It's about identifying disease. True's on top, in this case true positive, divided by everything, which is, in this instance, true positive plus false negative. Okay, sensitivity is about disease. Well, sensitivity has a partner. We call that partner specificity. And if sensitivity is about disease, the partner specificity must be about, well, clearly, the healthy people. These two give you complete coverage. Sensitivity focusing on identifying the disease, specificity focusing on identifying the healthy people, the non-disease, the people that are disease-free. If you get confused about sensitivity versus specificity, remember it like this. Aren't diseased people a little sensitive? Yeah, sensitivity goes with disease. The remainder, specificity, those are the healthy people. In my 2x2 table, therefore, now all I want to focus on is the right-hand column. I can safely ignore the left-hand column. No reason to focus on those. Those are people that are diseased. All I want are healthy people. Once again, now that we've carved out which part of the table to look at, let's apply our rule. What's the rule? True's on top, divide by everything. In this case, true negatives divided by true negatives plus false positive. Another way to say that, of course, is the true negatives divided by all the healthy people. Because once again, everything in this screening test calculation should be a healthy person. It is, after all, specificity. We're focusing just on the healthy individuals. Once again, the formula is straightforward. True negative divided by true negative plus false positive. And once again, the calculation is simple as well. Using the numbers from our table, it's now 60 divided by 100, or 60% specificity. 60% specificity, what does that mean? Simple. It means for every 100 healthy people, we're going to find correctly 60. Miss 40, find 60. Once again I ask, is this good, bad, or indifferent? Well, I'm now sort of in that indifferent range. There is some value here. I'm getting an incremental gain over the 50-50 random guess, but I'm nowhere near the range of correctness that I'd love to have, which is upwards into 90%. Nonetheless, if this was all you had in the universe, this is in fact what you would go ahead and use. Having nothing else, this is what you go ahead and use. So, we now know our test is a sensitivity of 80%, pretty good, although we'd like better, and a specificity of 60%. Not really good, but at least there's some value here. Now, wait. Isn't that enough numbers? I mean, come on, I can only talk to you about numbers for so long before you stop listening to me, and that part of your brain kind of switches off. So let's just take a mental break here in our conversation. Let me have you think with me about happier times to come in your life. Let's forget about all this stuff that we're learning. Let's think about happier times in the future. Let's say you've just finished your Step 1, Step 2, Step 3 exam, all passed with flying colors. You've matched in and completed a residency program of your choice. You're now out in thriving private practice, a wonderful private practice in the United States. One day, one of your patients comes in to see you, and with some anxiety, well, the patient says, Doc, I think maybe I caught HIV. I need to know. So you trot out the then current test to say whether or not the patient has HIV. And the results come back from the test, and the results say they do. Now you have before you one of the hardest jobs in medicine, delivering the bad news. Well, if you read the research on delivering bad news, you find some differences. Not everybody agrees, but there are some consistencies. One of the consistencies is, whenever you deliver bad news, always warn first. In short, don't come in and say, here's the news. Always warn first. Say, I have bad news, and then pause, and then deliver the news afterwards. That initial warning and pause lets people in some sense brace themselves. They're in a much better mental position to hear and deal with the bad news as you deliver it. So, your patient got a positive test result. You walk in the room to deliver this bad news. As you walk in the room, the patient is pacing back and forth. When you deliver this bad news to your patient, should you be sitting or standing? Well, the right answer is, of course, you should be sitting, and the patient should be sitting or standing. Well, of course, the patient should be sitting as well. And who should sit first? Well, again, obviously, the patient should sit first, and the doctor should sit afterwards. And when you're sitting with your patient delivering this bad news, how should we arrange the furniture? Should the chairs be face-to-face, side-to-side, or maybe even back-to-back? What do you think? Well, of course, face-to-face. You're going to have a conversation with someone. You really want to be able to look them in the eye, talk to them face-to-face. You want to arrange the furniture so you can do that. Look them straight in the face, so you want to be right across from them. And, well, how close should the furniture be when you're delivering this bad news? Well, let's see here. What do you think? About half an arm's length, arm's length and a half, 2 arms lengths, 2.5 arms lengths, 3 arms length? What's the right distance for this interaction? Well, it turns out the best answer is 1.5 arms length. 1.5 arms length. Why? Well, when you're 1 arm's length, people feel you're too close. Someone can reach out and grab you and you don't have any warning that they're coming. When you're 1.5 arms length, there's still the ability to reach out and access somebody, but they can, in some sense, watch your movement and know you're coming. When you go to 2 arms lengths, you're just simply too far away, and it becomes harder to touch and therefore harder to engage. The right answer there is 1.5 arms lengths. And so, you have a positive test result, you have to walk in and give your patient the news. You walk in, the patient's pacing back and forth. You will arrange the furniture, chairs face-to-face, an arm's length and a half apart. You have the patient sit down, you're going to sit down, and then you're going to warn first. You're going to say, I'm sorry, I'm afraid I have some bad news. Pause. The test is positive. You have AIDS. As you deliver this bad news to the patient, what's the patient going to say next? Guaranteed, what's the patient going to say next? Right. Are you sure? Because denial is the first line response to this bad news. Of course it is, but more than that, not only is the patient in denial, they naively perhaps have asked exactly the right question. In those words, are you sure, what they've asked you about is what we want to now call positive predictive value. Positive predictive value simply says, given that I have a test result, can I believe the result that I have? Given that I know I have a positive test result, what's the chance this matches the reality that I'm trying to get a handle on based on this test? Now, once again, we're faced with the fundamental issue here that we were discussing before, and we'll discuss again over and over. I don't know whether this patient has AIDS. All I know is I have a positive test result. Whether or not this test result is significant in the sense the patient has AIDS is another question altogether. And we call that positive predictive value. Remember, numbers are not reality. You don't have reality, you have a number, a positive test result. And the question must be, what's the chance this positive test result is correct? To walk in and talk to the patient without knowing this information, if you really are following me, should be inconceivable. Because the conversation you'd have with the patient if the positive predictive value is 95%, or the conversation you'd have with the patient if the positive predictive value is 51% is totally different. 95% you have firm conviction that you're very likely to be right. 51% you realize essentially a coin flip. And even though you have a test result, your grip on reality is not that much better than a random guess. How are we going to calculate positive predictive value? Well, just from the pattern of the table, I hope this is apparent to you. We're going to be focusing now exclusively on the top row of the table. The top row of the table is where all the positives are. Therefore, we can safely ignore entirely, in fact, the bottom row of the table, which is nothing but negative. This is positive predictive value. And all we need to focus on for positive predictive value is nothing but the positives. Let's apply the rule. The rule is, of course, trues on top divided by everything. That is true positive divided by all the positive. True positive plus false positive. Notice everything in that calculation is a positive. Yes, it's positive predictive value. There's nothing but positives in the calculation for positive predictive value. The formula is, of course, straightforward, and the calculation is easy as well. The formula true positive divided by true positive plus false positive. The calculation, taken from the numbers on the table, it's going to be 80 divided by 120, or roughly 67%. What's the chance that I'm right? 67%. I'm right, said better, 2 out of 3 times. For every 3 times I run this test, I'll be right twice. Positive predictive value tells you the degree to which the test result you have is likely to match the reality. That's positive predictive value. Let's frame another simple scenario. You have a female patient comes in to see you. You're now out in practice. Female patient's been trying to become pregnant for several years without any success, but now, having missed her period in her menses cycle, with great excitement, she says, Doc, I think maybe I'm pregnant. Give me a test. So you trot out the test to see whether or not she's pregnant, and the results say, unfortunately, no, she's not pregnant. Once again, you have that hard job, delivering the bad news. Once again, you're going to arrange the furniture correctly, get the distance right, have the patient sit, you're going to sit, and you're going to warn first. You're going to say, I'm sorry, I know how much you wanted this, but the test is negative, you're not pregnant. And once again, as you deliver this bad news, what's the patient going to say? Well, obviously, once again, are you sure? Notice, once again, the patient has naively the ability to ask exactly the right question. This time, not positive predictive value. No, we have a negative test result, but negative predictive value. Once again, the calculation is very straightforward. We're now going to focus only on the bottom row of our table, where all the negatives are. We can safely ignore the top row of the table, where the positives are. Once again, let's apply the rule. Trues on top, divided by everything. In this case, true negatives divided by true negatives plus false negatives. Notice, please, everything in that calculation must be a negative, because it is, of course, negative predictive value. Once again, the formula is straightforward, and the calculation's relatively easy as well. Using the numbers from the table, we have 60 divided by 80, or calculates to 75%. Translated, the right way to talk to your patient, there's a 3 out of 4 chance that I'm right. If I run 4 of these tests, 3 will be correct, and 1 will be wrong, and telling me that I have a negative test result. Now, we've talked about 2 sets of screening test values. Sensitivity and specificity, one set, and then positive and negative predictive value, the second set. Here's how I want you to think about these two. We talk about sensitivity and specificity as, quote, pre-test probabilities. These are the probabilities I use to select my screening test. These probabilities, pre-test probabilities, are constants. They should be the same for the test in all populations used in all settings. They're basically pretest probabilities, what define the test, that make it what it is and give it the consistency. Consistency in this case across situations and populations. I care about, once again, pretest probabilities when I'm selecting the test I'm going to use. Positive and then negative predictive value, on the other hand, are called post-test probabilities. We care about post-test probabilities, well, after we have a test result. Once I know I have a positive test result, I don't care about sensitivity or specificity anymore. I care about positive predictive value. Once I know I have a negative test result, once again, I don't care about pretest probabilities. All I care about is negative predictive value. Notice what predictive value gives you is your degree of belief, your degree of confidence in the test result you have. Positive predictive value, it matters when a positive test result occurs. Negative predictive value matters when a negative test result occurs. Let's look at our test overall. Sensitivity, 80%. Specificity, 60%. Positive and negative predictive value, each 67 and 75%. What do you think about this test? Is it a good test? You like this test? Would you like to use this test on all your patients? No, the test is sort of so-so. There is some value here, some utility, but it's not nearly to the level we'd like to see. You'd like to see 90s or 95%, frankly, across the board. There is some value, but it's not quite as good as you'd like it to be. Now, it took us 4 calculations to find out this was a so-so test. But you know what? We could have done one calculation. A calculation that looks not at the rows, not at the columns, but a calculation, and the only one we're talking about, that looks at the table overall. I refer, of course, to what we call the accuracy or efficiency of the test. The accuracy, efficiency of the test simply says how often overall, on a percentage basis, am I correct? Not just correct in terms of the true positives, true negatives, how often am I right overall? Once again, and one last time, we're going to apply the rule, which is trues on top divided by everything. In this case, that's going to be true positive plus true negative divided by everything. True positive plus true negative plus false positive plus false negative. Now, what's a simple way I can write everything? Right, I can simply use n. True positive plus true negative divided by n, the sample size, is another way to talk about calculating the accuracy, or again, the synonym, the efficiency of the test. Once again, the formula is fairly straightforward there before you, and the calculation's fairly easy as well. In this case, 80 plus 60 divided by 200 gives you exactly 70%. Telling you in a single number what you gleaned from the previous four numbers, namely, the test is right more often than it's wrong, but you wish it would be right more often than it is. It says in terms of overall, I'm right 70% of the time, I'm wrong 30% of the time. Let's hold on to what we've learned. Let's try to combine it with what material we've talked about previously. Let's focus on the effects of incidence on sensitivity. What is the effect of increased incidence on sensitivity? If incidence goes up, what happens to sensitivity? Goes up, goes down, stays the same. As incidence increases, sensitivity goes, well, don't guess. Let's look. Let's look. Here we have the same 2x2 table that we've been using. 80, 20, 40, 60, the same numbers we've been using. In this simple 2x2 table, what is the incidence rate for disease? What is the incidence rate here in this 2x2 table? You ought to be having a hard time finding the incidence rate in this table because there is no incidence here. See, this is a screening test. And screening tests don't give us when people began having the disease. Screening tests measure or not whether somebody has or doesn't have the disease. There is no incidence. Remember that screening is secondary prevention, and incidence is about primary prevention. The question about incidence and sensitivity, therefore, is basically a nonsense question. There is no direct connection whatsoever here. Questions about incidence and specificity, those are nonsense questions as well, because there is, in this table, no incidence to talk about. All right, there's no incidence here. How about prevalence? How about prevalence? If disease prevalence increases, what happens to sensitivity? Prevalence goes up, sensitivity goes up, goes down, or stays the same. Well, first, let's take a look at our simple 2x2 table and decide what the prevalence is here. What is the prevalence as shown in our simple 2x2 table? All right, those of you looking at the true positives equal 80, please stop that. Because you have to look at not just the true positives, those are just the disease people we found, you have to look at all the disease people. So the prevalence is, I have 100 disease people out of 200 total people. The prevalence is therefore 100 divided by 200, 50% prevalence. Everybody see that? Notice the prevalence is in the marginals, not in the cells of the table. 50% prevalence. Okay, now, if prevalence equals 50%, this is an example, we have a nice and easy way to calculate accuracy. You simply do the following. If prevalence is 50%, sensitivity plus specificity divided by 2 will give you accuracy. I'll say that again. Sensitivity plus specificity divided by 2 will give you accuracy. In this case, 80 plus 60 divided by 2 gives you 70%, just like we had before when we did it by the larger formula. Please note this only works if prevalence is 50%. If prevalence is other than 50%, you have to weight each one of those calculated numbers differently. If prevalence is 50%, they're weighted the same, hence dividing by 2 accomplishes the goal. Okay, so we've talked about what prevalence is here. Now let's deal with the question about how prevalence relates to sensitivity and then specificity. As disease prevalence increases, what happens to sensitivity? Well, the answer is nothing. Sensitivity stays the same, and by the way, specificity stays the same. Here's the way I want you to remember this. Pre-test probabilities, sensitivity and specificity, do not change. They're constant even in different populations. If the prevalence changes, sensitivity will stay the consistent number it always is, and specificity will stay the same consistent number. Let me try to demonstrate this by having you look back at our 2x2 table. Instead of 100 cases of disease, let me add a 0. Now you can see we have 1,000 cases of disease. Well, since the two numbers in these cells have to add up to that marginal, then they must change as well. This 20 becomes 200. This 80 becomes 800. Go ahead, quickly calculate the sensitivity, and you'll notice it's the same. See, the numbers change, but the ratio is constant. You're still going to end up at 80%, even though the prevalence has gotten larger. Why? Because all you've done is take 80% of a larger base. That 80% stays constant. It's just the base that is shifted. The ratio stays constant, even though the number of diseased people may increase or decrease. Look over at specificity and notice the same thing. Specificity does not change as prevalence changes. Once again, pre-test probabilities are constant. They do not change. But wait, what about post-test probabilities? Concretely, what happens to positive predictive value with changes in prevalence? As prevalence goes up, what happens to positive predictive value? Well, as you can see from the table here, as prevalence goes up, positive predictive value should go up. Because instead of what we had before, 80 divided by 120, now we have, as you can see in the data I've mocked up here, 800 divided by 840. And even if you're bad in math, that's a much larger number, right? As prevalence increases, positive predictive value should increase as well. Now, if that doesn't convince the left side of your brain, let me take a moment and try to talk to the right side of your brain. Let's take the class here. Let's cut it down the middle so we now have two groups. Over here on my right-hand side, your population A. In population A, you have a known prevalence of disease. 1 out of 2 of you have the disease, 50% prevalence. Over here on my left-hand side, population B, you also have a known prevalence of disease. 1 in a million of you have the disease. You're 1 in a million. I now screen both populations. From population A, I get a positive. From population B, I get a positive. Quick, which positive do you believe more? Well, of course, you believe more the positive that comes out of population A. Why? Because even if the test we're using, the screening test that is utter garbage, a random sample from this population is so much more likely to give me a diseased person, 50% prevalence, especially when compared to the other population, 1 in a million. Why do I believe this population, this positive more? Because there's so many more diseased people, the odds of having a positive be true are simply so much higher. Once again, I screen. From population A, I get a negative. From population B, I get a negative. Quick, which negative do you believe more? Well, in this case, I believe more the negative that comes from screening population B. Why? It's again about the base rate in the population. Even if the test is utter garbage, a random selection is so much more likely to give me a negative person here. And so, with that demonstration, let's say it as a rule. As prevalence increases, positive predictive value tends to increase. As prevalence increasing, negative predictive value tends to decrease. Said differently, prevalence and positive predictive value are proportional. Prevalence and negative predictive value are inverse. As prevalence goes up, positive predictive value up and negative predictive value down. Please notice that while the pretest probabilities are not affected by prevalence, please notice the post-test probabilities are dramatically affected by changes in prevalence. In fact, once you realize what I'm talking about, you can't really get post-test probabilities unless you have prevalence. Now, what does that tell you? That tells you that you're pretty much going to know when you run a test what is the sensitivity and specificity. That'll be given. That's a known quality of the test. But the post-test probabilities, positive, negative predictive value, you're going to have to compute those for yourself. Because with changes in population, especially population prevalence, the positive and negative predictive value will change as well. So although sensitivity and specificity will be the same across all situations, positive and negative predictive value will vary widely across all situations. Okay, so now we have a sense about how to do the calculations for sensitivity, specificity, pretest probabilities, positive, negative predictive value, post-test probabilities, and accuracy, looking at the test overall. All these calculations are based on giving a screening test with defined cutoffs and simply calculating the meaning of those cutoff scores. I next want to look at this screening test issue slightly differently. Focus your attention on this, well, now infamous, I think, double hump diagram. This diagram has a dimension, horizontal dimension, going from high to low. This dimension gives us particular values. What we want to do is convert this into a screening test dimension. We do that by first look at the frequency distributions along this dimension. Here we have a distribution of well people and a distribution of disease people plotted with their score along that horizontal dimension. These are frequency distributions. Where the curve is short, that means we have very few people with that particular value. Where the curve is tall, it means we have a great many people with that particular value. And notice we have separated out here the well people, that's the solid line, and the disease people, that's the dotted line. You can further see that this horizontal dimension I've been talking about does a pretty good job of separating out well people from disease people because these two curves are visually distinct. You can look at them and clearly see one as separate from the other. But it's not a perfect separation. There is some overlap here. There are some people that have a score that are diseased and some people have the same score that are healthy. And you see that where you have the overlap between the two curves. What we've done in this diagram is come up with a screening test cutoff score, which is the vertical line you see right in the middle. The way to understand that line is everything to the right is a positive. Everything to the left is a negative. That's the value that determines positive versus negative. Well, as you look at that vertical line we've drawn, it does a pretty good job of separating out disease from well people because most of the disease people are correctly classified on the positive side as true positives. Most of the healthy people are correctly classified on the negative side, that is true negatives. The only errors we have are these two small triangles down there at the bottom. We have the small triangle, well people, misclassified on the disease side. Those are the false positives. And we have the disease people, misclassified on the well side. Those are the false negatives. Now, once again, look and notice that everything to the right of that line must be a positive. The only question is whether they're true positive or a false positive. Please note that everything to the left of that line must be a negative. The only question is whether they're true negative or false negative. One way to help yourself be less confused about this is to, as I suggested earlier, don't start with the trues or the falses. Start with the positive versus negative. Everything to the right is a positive. Everything to the left is a negative. Having explained how to read this diagram, I'm now going to go back through a series of application issues, some simple questions to let you build up your expertise in using this material. I begin with the question set that is shown in your syllabus. Here we have a 2x2 table presented and some accompanying text, so let me begin to read. A new screening test is applied to a representative sample of 1,000 people in the population. Based on the data presented in the following table, calculate the requested screening test measures. I look at the table, it says disease, well, positive, negative, and I'm very happy. Why am I very happy? Because this table is in the standard format. Disease on top with disease and then well, and screening test, positive, negative on the side. It's the traditional format with everything in the location I expect it to be. Now remember, the first thing you do when you see the 2x2 table is check that simple geography. Is everything where you expect it to be, or did they rotate the table? Okay, now that I know I have a standard traditional table, let's go through and do the questions as presented in your syllabus. Question 21. What is the sensitivity of the screening test? Sensitivity of the screening test. Well, let's see. Sensitivity is about what? Health or disease? Right, disease. And so how many total disease people do I have? Right, 100. And so the answer must be B. Don't worry about the numerator. The denominator gives you the answer here. There's only one of these divided by 100. That must be the answer, therefore B. 90 out of 100 is sensitivity. Let's go on and do question 22. What is the specificity of the screening test? Well, let's see. How many total healthy people do I have? I have 900. Therefore, the answer must be H. Once again, you don't really have to worry about the numerator here. The denominator by itself gives you the answer. There's only one of these divided by 900, and therefore only one of these could be the right answer for specificity. The answer here is H. 23. What is the positive predictive value of the screening test? Positive predictive value. Well, how many total positives do we have in the screening test? As I look here, it looks like 150 over in the marginal. And since I only have one answer divided by 150, that is A, then A must be the correct answer for positive predictive value. 90 divided by 150 gives me the correct positive predictive value of this test. Please notice, as always in epidemiology, I keep looking at the denominators first. That's always where the action is. That's always, for clarity, where your thinking and vision should go first. Next up, 24. What is the accuracy of the screening test? Well, accuracy is about the table as a whole. And since I have 1,000 people in the table, it must be something divided by 1,000. Well, as I glance over my options, I have 4 possibilities. So I can't simply pick based on the denominator. But it's a fairly easy answer because the true positives are 90. The true negatives are 840. When I add those together, true positive plus true negatives, clearly that's some number over 900. Therefore, the answer is I. 930 divided by 1,000 gives me the measurement for the accuracy. 25. What is the number of false positive test results? Well, all the positives must be on the top row. And since we said the true positives were 90, the false positives, what's left over, must be 60. The answer here is E in terms of the false positives. And finally, what is the prevalence of disease, assuming a representative sample? What is disease prevalence here? Well, that's fairly straightforward. We have 100 total disease people out of 1,000 of the population that we're talking about. 100 out of 1,000, the answer here is K. Each of those questions should have been, I hope, ridiculously easy. This is just a quick run to make sure you have the basics of these calculations, to make sure you can do the actual mechanics. With that behind us, let's move on to something a little bit more exam-worthy. I'm going to draw your attention now to the graph at the top of the next page. This graph gives you the double hump diagram and a question about it. Let me read the question with you. The Centers for Disease Control and Prevention is concerned about optimizing the detection of disease that poses a serious public health threat. CDC health officials are considering lowering the usual screening test cutoff from X to Y, from X to Y. Notice I repeat myself on that. And the reason, of course, is to make sure that I go from X to Y, not from Y to X. If I go the wrong direction, I almost certainly get the wrong answer. Now, unlike on the real exam, there's multiple questions about this graph. The exam only gives you one question per stimulus, but let's walk through the questions together to make sure we understand what's to be seen and what's going on in this diagram. I have disease over on the right. I have well over on the left. Okay, that's the traditional format. You can see that X is the line right in the center between the two, and Y is therefore the line over one block to the left. With that in place, let's take a look at our questions. Number 27. Moving the cutoff in the manner being considered by the CDC causes the number of false positives to do what? What happens to my false positives? When I move from X to Y, a lot of the healthy people that were before correctly classified as true negatives now become classified as false positives. When I'm at Y, I'm saying positive to the right, negative to the left. You can see that all those people between X and Y of the healthy distribution who were classified correctly before are now incorrectly classified. Incorrectly classified, that would be false positives. The false positives, of course, are increasing with this move from X to Y. Question 28. Moving the cutoff in the manner being considered by the CDC causes the positive predictive value to do what? Well, here's a thought. If the false positives are increasing, then the positive predictive value must be decreasing. Remember, the way to get perfect positive predictive value is to have no false positives. As my false positives increase, I must of course be decreasing my positive predictive value. I'm doing a better job at Y of selecting in disease people, but we're doing a worse job of correctly classifying the well people. Therefore, more false positives is worse positive predictive value. Number 29. Moving the cutoff in the manner being considered by the CDC causes the accuracy to do what? Well, when I move from X to Y, as I mentioned, we're doing a better job at classifying disease. So that little triangle of disease people on the left that were misclassified at X are now correctly classified at Y. I've in short lost some false negatives, and that's a good thing. But I have to pay a price for that. Because now that much larger section of well people that were true negatives correctly classified are now misclassified. Therefore, I have an increase in false positives. Since the key issue for accuracy is to have the fewest possible falses, well, I'm getting rid of a few false negatives, but I'm gaining a lot more false positives. Hence, my total falses, false positive plus false negative, are going up. Therefore, when I move to Y, my accuracy will decrease. My accuracy will be less than it was when I was at X. Number 30. Moving the cutoff in the manner being considered by the CDC causes the sensitivity to do what? Sensitivity to do what? Without a hope, it's fairly straightforward. Sensitivity is increasing because when I'm at Y, I'm doing a much, much better job of correctly labeling all the disease people. Now, understand the fact that I'm misclassifying healthy people doesn't matter here. The fact is I'm correctly classifying disease people, and that's what sensitivity is about. So Y gives us better sensitivity. 31. Assuming that everyone receives a positive test result is referred for medical follow-up, moving the cutoff in the manner being considered by the CDC will cause the number of screened people referred for follow-up to do what? The number of people referred will go up or go down. Well, the right answer, of course, is they will increase. Because all those people between Y and X who heretofore were not referred for follow-up now all will be referred for follow-up. I have all those people in that area between Y and X who before were not referred, now will be. That will be more people referred. The number of people referred for follow-up will go up as I move to Y. And finally, one additional question on the top of the next page. Using the same graph, let's do question 32. Question 32 says, at cutoff X, sensitivity is what? What is the sensitivity at cutoff X? What do you think we should do here? Well, we're going to get there by using the knowledge we have and extrapolating what the answer must be. Look with me, if you will. If you walk all the way over to the tail end of the disease distribution on the left, right smack in the middle of the healthy distribution, well, from that point right a little bit to the left of Y and going all the way to the right, you would have all the disease people correctly classified. So that point, a little bit to the left of Y, would be the cutoff point that would give you perfect sensitivity, 100%. On the other hand, if I move smack in the middle of the disease distribution over to the right of X, you can see that right smack in the middle of the disease distribution, at the median, I'd have half the disease people one side and half the disease people on the other side. Therefore, at that point, right in the middle, sensitivity would be 50%. So if on the left it's 100%, and over on the right it's going to be 50%, X is some number between 100% and 50%. Therefore, looking at your answer choices, the sensitivity X must be 85%. Why? Because the only answer within the specified range. Notice it's going to be 85. I wouldn't choose 75 because these are slope curves. It's not going to be right in the middle. It's going to be a little bit off center, closer towards the upper level. 85% there is the answer, letter B. Being able to deal with these double hump diagrams is so important. I'm going to look at another version, ask you another set of questions. Take a look up on the screen here, and again you see the same presentation. We have a distribution of healthy people on the left, distribution of diseased people on the right, with some overlap. But this time we marked for you 5 potential cutoff points along the horizontal dimension. Now that horizontal dimension again could be anything you want, but for purposes of exactness we made it to be blood pressure here so you can see what it is we're talking about. The question is, which of the cutoffs, A, B, C, D, E, should you use if you want to have optimum sensitivity? Optimum sensitivity. Well, let's see. Sensitivity means I want to correctly classify all the diseased people. That would be B. Now notice, the fact that that appears right smack in the middle of the healthy distribution is just the devilish way the diagram is drawn, because what matters is not the height of the healthy distribution. What matters is being at the tail end of the disease distribution. From B over, everybody is a positive. Therefore, all the diseased people are correctly classified. All right, if B is optimum sensitivity, what is optimum specificity? Well, that would be D. Because once again, from D over, everything's a negative. Hence, at D, all the healthy people are correctly labeled. True, negative. All right, well, you can guess what's coming next. How about positive predictive value? Which cutoff, A, B, C, D, E, gives you optimum positive predictive value? Well, before you can answer the question, you have to stop and remind yourself, what do we mean by positive predictive value? Simple. Positive predictive value, when I'm right, everyone I say has a disease actually has it. When I'm optimum, everybody I label, declare as diseased actually is diseased. And that becomes true when D is the cutoff. Because from D, dog, over all the way to the right, I have nothing but diseased people. Now with that in mind, let's look at the contrast between sensitivity, which says get me all the diseased people, and positive predictive value, which says give me only the diseased people. All disease, only disease. All disease, only disease. Sensitivity, positive predictive value. One of the common mental errors people make in screening tests is they confuse together sensitivity with positive predictive value. Look again and see visually they're nothing alike. Sensitivity says bring me all the diseased people, and if you're bringing a bunch of healthy people at the same time, I don't care, as long as you get me all the disease. Positive predictive value says bring me nothing but diseased people, and if you miss a bunch of diseased people, I don't care, as long as everybody you bring me is actually diseased. All disease, we're talking about sensitivity. Only disease, we're talking about positive predictive value. How about, same diagram now, negative predictive value? Well, let's see. In negative predictive value, everyone I say is disease-free, that should be true. And that becomes true at B. From B over to the left, everybody who I say is healthy actually is. And now, once again a contrast, this time between specificity, give me all the healthy people, and negative predictive value, give me only the healthy people. All the healthy, only the healthy. All the healthy, only the healthy. Specificity, negative predictive value. Once again, although people commonly confuse these in usage, they are nothing alike. Specificity says give me every healthy person. I'm willing to take a bunch of diseased people with that to make it true. Negative predictive value says bring me nothing but healthy people, and I'm willing to leave out a bunch of healthy people to make sure I have nothing but healthy selected in. So, the tendency to confuse together sensitivity and positive predictive value, it's wrong. Don't do it. The tendency to confuse together specificity and negative predictive value, it's wrong. Don't do it. Now wait, there is a pairing, however, to be made between the pre- and the post-test probabilities. Look at your diagram. At B, as I look over to the right, I have all the diseased people, perfect sensitivity. Well, wait, if I have all the diseased people to the right of the B line, what do I have left for residual to the left? Oh, that's easy. Only healthy people, by which I want you to see that sensitivity goes with negative predictive value, not positive, but negative predictive value. At the same time, when you go to D, from D over to the left, I have all the healthy people, perfect specificity. Okay, with that in place, what's left looking over to the right? Well, the residual is only diseased people, by which I want you to see that specificity goes with positive predictive value. Let's do that again. Sensitivity with negative predictive value, specificity with positive predictive value. When I have all the diseased people, all I'm left with for residual is healthy people. Sensitivity with negative predictive value. When I have all the healthy people, specificity, all I'm left with is diseased people, positive predictive value. I want you to see these as basically heads or tails of the same coin. We're simply chopping up the diagram so we have sensitivity looking one way, negative predictive value looking the other way, or if you prefer, so we have specificity looking one way and positive predictive value looking the other way. The way to remember this, a simple mnemonic, N with N and P with P. Sensitivity goes with N negative predictive value. Sensitivity, negative predictive value. Specificity goes with positive predictive value, P with P. Specificity, positive predictive value. So, the take-home question is simple. You want to select a test which at the end of the day will have the best possible positive predictive value. Should you select a highly sensitive test or a highly specific test? The answer, of course, as you see on the diagram, is a highly specific test will give you the best positive predictive value. That means specificity and positive predictive value rise and fall together. At the same time, sensitivity and negative predictive value rise and fall together. Let's wipe the slate clean and ask you, using the same diagram, a different set of questions. Looking at the diagram as presented here, please tell me which cutoff score, A, B, C, D, E, gives us optimum accuracy. Which cutoff score gives us the highest accuracy? Well, the answer is, right, of course, C. Because at C, I've done the best balancing act between classifying disease and healthy. I've done a job that gives me the highest chance of being right. Well, let's ask a different question. Which cutoff score, A, B, C, D, E, gives me the fewest falses? The fewest falses. Well, that's the same answer. Put these two side by side. Highest accuracy, fewest falses, Aren't those the same thing in different words? See, when C is the cutoff, what I'm saying is everything to the right of that C line is a positive. I'm saying everything to the left of that C line is a negative. Therefore, the only misclassifications I have are these two small triangles you see down at the bottom. This small triangle over on the left-hand side, this is what? Well, clearly false, but false what? False negative. It must be negative. It's on the left-hand side of the dividing line. Everything to the left is a negative. And this small triangle over here to the right, this must be false, of course, false positive, because everything over to the right side must be a positive. Let's change the cutoff. Instead of C, cat, let's change the cutoff to be D, dog. If D is now the new cutoff, what has happened to my number of false positives? Answer, false positives will now decrease. Decrease to what? To 0. Because all those healthy people that were misclassified will now be correctly classified. The false positives at D have been converted to true negatives. But look at the price I pay for doing that. When I'm at D, what happens to my number of false negatives? Well, now they've exploded tremendously. Now, instead of that small triangle, false negatives, the entire 1/2 of the distribution of disease people, from B all the way over to D, all of those people are now false negatives. Although I lose my false positives, a good thing, I pay a disproportionate price, I gain too many false negatives, a bad thing. In general, wherever right below where the two curves cross is going to be your optimum accuracy, your highest efficiency, to use the synonym. And in other words, wherever the two curves cross is going to be what minimizes my falses. Take a look at the C line again. Wherever you go to the right or to the left, you can see that the total falses must increase. Okay, with that, we have a question I want to turn your attention to. Question 34. Let's walk through this question together. A 55-year-old man visits his primary care physician with a complaint of urinary infrequency. Examination finds a 1-centimeter nodule in his prostate gland. Well, that's not good. Physician orders a PSA serum test. By common standard, a PSA level greater than 4 is considered abnormal. Using this standard, this test has a sensitivity of 80% and a specificity of 90%. A recently published epidemiologic article found that in a cross-sectional study, 10% of the men in this age group have prostate cancer. The result of the patient's PSA is 7. What's your best estimate of the likelihood this man actually has prostate cancer? Now, this is by far the most complicated kind of question we've looked at so far, but let's tackle it together. The first issue is, what's the most important information given in this question? You have to understand what the question's really about. Well, let's unpack what we're given here. The patient's PSA is 7. The cutoff is 4, so he's over the cutoff. Therefore, he has a positive test result. Therefore, your best estimate of the likelihood this man actually had prostate cancer, translated, is what's the positive predictive value? We want the positive predictive value because it's a positive test result. Now, you're given three percentages here. Sensitivity is 80%, specificity 90%, and finally we have 10% of the men in this age group have prostate cancer. Which is the most important of those three numbers? Well, the answer is it's the prevalence. The prevalence, 10% of the men have prostate cancer. Stripped down of all the words and reduced down to the fine-grained detail here, all we're really asking you in this question is simple. Do you remember that when you calculate positive predictive value, you have to take prevalence into account? You remember that? If you do, you should get this question right. If you don't remember that, you're certainly not going to get the question right. How would you proceed here? Well, there's some formulas I could teach you to answer this question, but I never do that because experience shows you don't remember always the formula you need during the exam. What we're going to do, therefore, is something I know you can always remember. We're going to construct a 2x2 table because you can always construct a 2x2 table. On the whiteboard you're given in the exam, you're going to draw two intersecting lines which are going to frame the table. You then label this using the traditional format so you have all the right things in all the right places. Now, on the real exam, I wouldn't put in these labels. I would just assume that everything's where it's supposed to be in the sequence. And now I'm going to add 1,000 people down here as the sample size for my table. Why 1,000? Because it doesn't matter what number I start with. What matters is the ratios, so the total number doesn't matter. I'm using 1,000 because it's simply an easy number to work with that features a lot of zeros. Now, the crucial step. It says 10% prevalence. In order to proceed, I have to insert prevalence into my table. Well, if the total sample is 1,000, 10% prevalence, that means I should have 100 people with disease. Since the marginals have to add to 1,000, that means the remaining number here must be 900. And now we're pretty much home free, because all we have to do is take the numbers for sensitivity and specificity and reason backwards in order to get the right numbers to fill the cells. If sensitivity is 80%, well, the only way that can be true given 100 disease people is if I have true positives equal 80 and I have false negatives equal 20. Therefore, 80 and 20, look at it again, gives me my 80% sensitivity. If specificity is 90%, well, the only way that's going to work is if my true negatives are 810 and my false positives are 90. Now, frankly, I don't really need the number 20 and the number 810. Those are in the negative row. And since what I'm worried about is positive predictive value, I don't even really need those values. I've written them in here so you can see what we're doing in the table, get a sense of completeness, but really it's the numbers up on top I need. The 80, that is 80%, and the 90, which is, please note, 10% of the base of 900 healthy people. Why is that 10%? Because if I have true negatives being 90%, clearly what I'm left over with to complete the column is 10%. What I now have is 80 and 90. I add those together to get the marginal of 170. But now I don't even really have to do a calculation here. I can estimate this and then pick an answer based on what the results are. Notice I have true positives of 80. Notice I have false positives of 90. Hey, I have fewer true positives. And so, is my positive predictive value going to be a number above or below 50%? The answer, of course, is below 50%. It's going to be a lot below or a little below. The answer, of course, is going to be a little below. Without doing the math, you can see, given our answer choices, the answer must be 47%. Notice I'm counseling you not to do the math. Look at it, estimate, get the answer, and get out and go to the next question. Because when you're doing an exam, you're in a hurry, you're anxious, you make stupid math errors. And let's go back over this again. I'm just going to talk about one more time so you get a sense of what we did. First, we have to, in order to get to positive predictive value, having been given the pretest probability, sensitivity and specificity, I have to construct a 2x2 table. I do that by starting with framing the table, and then I give myself 1,000 people to work with. I then have to anchor this in prevalence. That's 100 out of 1,000. That's 10% prevalence. I can then use that to figure out what is the sensitivity. Well, sensitivity is 80%, so it must be 80 and 20. Specificity is 90%, that must be 810, the true negatives, and 90, the false positives. I now only need the positives on top. It's going to be 80 divided by 170, or just below 50%, 47%. Now, is that a hard question? Yes, it actually is kind of a hard question, but please note it's not an impossible question, and it's one that all of you should be able to answer correctly. I'd like you to be comfortable with this kind of calculation, so I do have a suggestion for you. When you're done here listening to me today, sit down and take this table and let's change some parameters and recalculate and watch what happens with the recalculation. Instead of, for example, having 10% prevalence, make it 30% prevalence and redo the calculation. You'll find your positive predictive value goes up rather considerably. Go ahead and make your sensitivity into 90%, and you'll see again your positive predictive value goes up, although not nearly as much as when you modify the prevalence. You notice you can also use the same table to answer a question about the negative predictive value of the test, which you can tell at a glance must be a really high number in the high 90s, just because of the sheer magnitude of the ratio between the cells. With that, I have one more thing I want to talk to you about, and then we'll leave off our conversation about screening test. The last thing I want to focus you on is this simple diagram which defines for you what we mean as we talk about receiver operating characteristic curves. Receiver operating characteristic curves are used to decide which of several possible screening test dimensions should be used as a screening test. These curves are always diagrammed, so we have, as in the present case, sensitivity, that is the true positive rate on the vertical, and 1 minus specificity, that is the false positive rate on the horizontal. Please note, I didn't say specificity, I said 1 minus specificity. All right, the question here is, which of these three possible screening test dimensions, A, B, or C, is the best dimension to use? Well, in case you're not clear, A is essentially worthless. As you look at your diagram, you can see why. For every increase in a true positive along the vertical axis, we have a corresponding increase in a false positive. Every benefit is outweighed by a negative, therefore there's no net gain by that. As you look at line B, you can see that's actually pretty good, because we do have an increase in true positives before we accept a corresponding increase in false positives. But the best of these three options is clearly C. C gives you a tremendous increase in true positives, up to roughly 50%, before we have to accept really any false positives at all. So how do you remember this? Simple. The curve, given a set of options, that bows the most to the upper left-hand corner is going to be the best screening test dimension. C here fulfills that criterion. Therefore, given these three options, C is the best screening test dimension. Well, holding on to this same diagram, let's ask you a different question. Which one of these screening test dimensions, A, B, or C, has the highest accuracy? Which one of these has the highest accuracy? Well, the answer to that is, of course, once again, C. How can I say that so certainly? Because the area under the curve gives you the accuracy. The area beneath the line, under the curve, is, well, simply geographically a representation of the highest accuracy. You can see, for example, that the accuracy for curve A is 50%, not really very good. You can see, eyeballing it, that the accuracy for curve B is maybe 70%. You can see the accuracy for curve C is closer to maybe 85 or 90%. The curve that bows the most to the upper left-hand corner is the best of the screening test dimensions, and the area under the curve gives you a, well, geometric representation of what we mean by accuracy. And with that, we've finished talking about screening test. Now, we spent a bit of time talking about this because, again, this is important content. The question is not, will you have questions on screening tests? You, of course, will. The only question is, how many will you have? Although it varies between exam to exam, I'd expect each of you to face maybe at least 3 questions, and sometimes as many as maybe 7 or 8 questions in this area. I'd like you to spend time with this content, not so you can maybe answer the question, but when you're so comfortable with the material that when it shows up on the screen before you, a smile comes to your face. You treat this as good safety zone in the middle of the exam, not as another one of those hard questions that you have to solve.